One of my favorite interview questions is, how would you implement calculating factorial? The wonderful property behind such a simple problem is that it puts literally everyone at instant ease right from the get-go, because everyone knows how simple factorial is and hence how simple the implementation will be. But as an interviewer, you can then use this known and easy domain to explore further concepts in terms of algorithm design or sort of various computer science related subjects, nuances around compilers, runtime, algorithm memory complexity, or what have you. So in the next few minutes, I'll try to just whiz through as if an interview format live, just having a dialogue between the interviewer and candidate that sort of illustrates how to explore fundamental computer science topics through a simple factorial implementation. Obviously just covering a few things that pop into my mind, but still should be quite interesting. So how would you implement a factorial? Well, in Java, I would start by creating a new class. I'll call that class factorial calculator. And for factorial, it would have one public method. It returns a number. When we talk about factorial, we talk about whole numbers, so integers. So the method for calculating factorial will return an integer. The name will be factorial, but it could be something like calculate or calculate factorial as well. And it will receive a parameter of integer as well. I guess the most straightforward way of calculating factorial is through the for loop. So first we'll begin by introducing a helper variable result that we'll use to return the result from the function method. Really, it's a function method. Well, in Java terms, it's a method, but we are really talking about a function here, something that receives a parameter, doesn't have any side effects, and returns a value. So the for loop would look like, pretty much the simplest thing is that we initialize an integer I, and we set off by initializing it to 1, and we go until n. And in each loop we increment I by 1, and in every loop we multiply the result by I. Just for the sake of this exercise, I will quickly implement a main method just to showcase that the below method actually works. In a live interview session, this could be happening as well. So we'll instantiate the factorial calculator object, and we'll call the factorial with the number 5, which should return the result of 120, and indeed it does. So a couple of questions that now that we've proven that we have working implementation is, again, just off the top of my head, one interesting bit is the selection of the type. So the candidate, which is me in this case, has selected an integer type. So the first question is, well, what are the limitations in terms of n? What are the values of n that this factorial will still handle and return us the safe result? So int is a data type which in Java is defined as a 32-bit integer, signed integer. So you have 32 bits that represents pretty much like a little bit north of 4 billion values, but since it's signed, we're talking about a little bit north of 2 billion values. So any result past 2 billion will be pretty much guaranteed incorrect. And so one of the questions that you could pose to the candidate, it's a little bit more of a math question, I would guess, is, well, how would you find out, given int, given the data type int that we are working with, how would you find out the limit of n? So what's your largest n for which this method still returns a valid result? What's the number n where the result will yield a larger value than approximately 4 billion. And just it can be a very quick question just to gauge the candidate's sort of approximating ability. I would guess 15, just off the top of my head. I haven't checked, but 15 is pretty much a good number, because once you are about 10, then in each cycle you are adding an order of magnitude to the scale of the result. So 4 billion, a billion has x digits, is it 9 digits? And so pretty much very quickly, once you get to n equal or larger to 10, the results will basically snowball into a very large number. How would we get past this? Could be a question. Well, the simplest answer is just using long to begin with. Well, actually, this could remain int, and of course, then having the intermediate result being defined of type long, and long is a 64-bit integer, so it's much larger. Now, if we want to go even beyond long, then the question would be, well, what's more sensible after long? How would you do it? Well, probably in Java land it's big integer, but then it gets very language dependent, because you might argue, well, actually we'll switch to doubles or something like that. But then we are in floating point land, so that's then very specific to the language and more nuance around the requirements for this factorial. So that's for the data types, really. Another question I could pose to the candidate is, well, why are you using this infix, or rather prefix notation for incrementing I? Why not do I++? And the answer there is, well, it's simply, generally it's more optimal to use ++I in such situations where you don't want to use the sort of the intermediate return value of the value object, or the value type in this case. So it's more optimal is the short answer. But then the candidate or the interviewer could ask, well, does it matter in this case? Does it matter if I do I++ or ++I? And the answer is no, it doesn't really matter, because the compiler will be smart enough to basically optimize away the intermediate calculation for when I do I++. Well, it almost certainly does optimize it away, so that would be the answer. Another question could be, could you implement this in a different way? And the answer there is, yeah, sure. We could implement this using a while loop. And so the implementation there would be like factorial, I'll just call it 2 int n. Again, yeah, we'll define a result as an intermediary value type to hold the result, and we will just go while n is larger than 1, do result times equal n minus minus. So if we just test that pretty much should have the same result as the first implementation, with the small caveat that it's using a while loop instead. So how would you compare these two implementations? Well, in terms of their speed, they pretty much should be the same speed. The one difference, so the advantage for the first one is that you aren't messing with the parameter's value. It's not the best practice. It's not a best practice to modify parameters passed into a function or a method. Just because then if you have a non-trivial method, you might rely on the value of the parameter not changing or being immutable. So as a best practice, we could mark this parameter here as final, but we can't mark it as final here because we want to change its value. However, the advantage of the second implementation is that you don't have this sort of line where you are introducing yet another value into the implementation. So here, look, you have an integer that represents the parameter. You have a longing in this case that represents the result, and then you are defining a third data type I, and then equals to a initializing value, a smaller equal comparison, and then the plus plus. In the second method, your I completely drops out of the picture. You don't have to define its type, you don't have to initialize it, and you don't have to increment it. You have to increment the end though. So it's a little, so the second one is a little bit simpler because you don't have to deal with I, its type, its initialization, but you do have to consider the fact that you are modifying the parameter, which I would say you pretty much always want to avoid unless you have very good reasons, like there's a list coming in or something like that, where you are just really modifying the contents of the object. Okay, the interviewer at this point might ask, well, is there any other way to implement factorial? And obviously at that point, if the same question is being asked multiple times, then it should hint that you are going down the wrong path. The interviewer is meaning something else, and what the interviewer means in this case is probably they want to hear, yeah, I could implement this using recursion, and that's pretty much where most of it ends, because recursion isn't something that's typically tested on interviews, but it depends. Recursion isn't something that is too interesting generally. I mean, if you look at interview questions, you'll come across it, but in day-to-day like web development or mobile application development, Android, iPhone, iOS, things like that, I haven't really come across much recursion, if at all. Recursion is mostly when you are doing algorithms related to recursive data structures like trees and things like that. And even then, languages provide powerful libraries, so typically you sort of get away with not really implementing anything at all pretty much most of the time. But for the sake of the exercise, let's do the factorial recursive implementation. Which again will receive a parameter n, and it will return, well, what will it return? It will return twice. So the way factorial works is you keep calling the same function within itself with a mutating parameter, and you have a stop condition, a well-defined condition at which point that recursive call stops. For factorial, that call is, trivially speaking, 1. Once you hit n equals 1, then you just return 1. So the implementation goes something like this. If n equals 1, then return 1. Else return n times factorial recursive n minus 1. Okay, so once you hit 1, you return 1. Otherwise, you do n times factorial n minus 1. So the disadvantage is this is recursive, so it will eat up your stack. The advantage of this implementation is that it's much more akin to the mathematical definition of the factorial of n. So it's sort of nicer to read. It's easier to derive the requirements based on the third implementation than it is to derive the requirements based on the second or the third implementation, where you have to sort of parse what the for loop actually does. Here it's much nicer, and you can even simplify this by getting rid of the else, because this if has a return, so you can get rid of the else and do it like this, and this is even nicer. Let's test this. So we'll call recursive here, recursive, and we should get 120 for this one as well, and we do. The other thing that you might be, as a candidate, asked about is, well, okay, nice, this is a 1, 2, 3, 4, 5 lines of implementation. Could we optimize this in any shape or form? Well, and the answer is, if we think about it a little bit more, then the answer is yes. I mean, it's not a huge optimization, but hot code, so code which gets called all the time, even a very small optimization might have significant impact. And by significant impact, I would mean a couple of percentage point improvements. The optimization I'm talking about is to simply use 2 as, oops, not here, but here actually. You could start from, so your result is already 1. So if n equals 1, then you just want to return 1. So if you initialize from 2, then this will fail at the first run, and you will still return result equals 1, despite the fact that you are starting. So basically, you are getting rid of one unnecessary loop execution if your n is bigger or larger than 1. So if I run this just to prove that it still does 120, here's your proof. So that's a small optimization we could do. Another question could be, well, what about the corner cases? If n would be smaller than 1, that's essentially a non-defined factor isn't defined for that. Sort of typically when you think about the, let's say, naive definition of the factorial, anything below 0 wouldn't make a difference and wouldn't produce a value, an actual result. So you could say something like, well, if n equals, if n is smaller than 0, then, well, we need to sort of say that there was an error. And so you can go about this in 2 ways, sort of the old style way of, well, this is undefined, so I'll just return -1. And the nice property is that it's sort of, it's a function. If you think about it purely in terms of functions, then -1 is sort of a C-like way of saying, I don't know what I should return, so you'll get -1, which would in this case signify like an error state. And then the client could go, the calling code could say, if the result from the factor is smaller than 0, then I know some sort of error has happened. A more Java way, of course, will be to throw an exception. And in this case, we would probably throw a illegal argument exception. Illegal argument exception. And we would, say something like factorial is only defined for n larger or equal than 0. So something like that. Now you could do a checked exception. You could come up with a checked exception, and then your code would say something like, this throws a blah 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 exception, and then the client calling code would have to always cater for catching the appropriate exception. In our case, this would be an illegal argument exception, and I would reckon is the client's code fault that it provided a n which would be smaller than 0, and a runtime exception is the proper choice to make. So that's for edge case handling. The last thing I would finish with is, if this would be a live coding session, is, well, how would you test this? And obviously I would create test classes. And so the test class would be named test factorial calculator. And you would implement a public void test factorial equals 0, say. We do the imports, and we basically assert from org JUnit, we asserted, okay, we assert that, say, for 0, when I do instantiate and call factorial with 0, I indeed get, well, actually I get 1, I don't get 0, I expect 1. And then say factorial calculates 5, and the result there should be 120. And if I run this, actually I can run the whole project as a JUnit test, and then I get 2 beautiful green tests. Right, let me just finish with, okay, I guess one of the final questions would be, how would you test how would you unit test the the edge case? So in this case, the illegal argument exception, and it's pretty easy. You go, I'm expecting to see an illegal argument exception here, and let me just copy paste this. This factorial test negative factorial throws exception, and then I will just literally just call the code with -1. Expected. Alright, let's run this. Okay, all 3 are green. So that's pretty much 20 minutes, more than 20 minutes being spent on just exploring some of the calculation around factorial, different ways of implementing it. Right, the last question would be, what's the memory complexity? And the memory complexity is constant, because no matter how large n is, the memory will, the amount of allocated memory will be constant, no matter what the size or scale of n is. And so we have a constant memory complexity. In terms of execution or computation complexity, you basically have a linear complexity, because the larger the n, the more operations you'll have to execute, and that will scale linearly with n. That's it. Thank you.